All right, I'm going to try to explain the normal distribution here a little bit. So, the normal distribution is a bell curve. I'm going to try to get my stylus to work here. There we go. All right. So, there is a special normal distribution, which I'll draw in blue, called the standard normal. These two shapes of the distributions are very similar. All right, they're still bell-shaped. The key is the standard normal, which is in blue, is always centered at 0, with a standard deviation, sigma, that's that little funky symbol right there, that equals 1. And it's centered at 0, which is our mean, mu. So one of the formulas in the book is z equals x minus mu all over sigma. The purpose of this formula is to allow you to take any normal problem and turn it into a standard normal, right? Because you're going to take some mean and some standard deviation, and x is always your event. We learned about events in week 1, right? So for say we're finding the probability that some random variable, which we call capital X with these lines, is less than or equal to some event x. It's this x value that you put right there. And saying you have a mean of 50 and a standard deviation of 4. Right? So here's our normal distribution where it's centered at 50 instead of 0. The reason we use to go from a normal to a standardized normal, right, to go from here to here, is so we can use the tables. All right, so if you're going to use the tables, you have to calculate your z-scores, right? And you find that by taking some event x. So let's go on to our next page here so I can show my math. Say we want to find the probability that some random variable is less than or equal to 40 when our mu is 50 and our standard deviation is 4. All right, so if we go back here, that is where our first distribution. So this is where we are, right? So this value now is 40. I can either use the z-score and calculate, so I can use the tables, right? So if I want to do that, z equals 40 minus 50 all over 4. If you're going to type this all at once in your calculator, then I put parentheses in here, because 40 minus 50 is negative 10 over 4, right? And then 10 divided by 4 equals negative 2.5. Right? And then you'd go to your table and find that, and that would give you the probability that x is less than or equal to 40. However, what we can now do, I don't know where I get it from, is if we use technology in Excel, you can type in equals norm dist, and then I guess I'm going to run out of room. Go bring up some parentheses. You put in your x value, 40. Put in your mean, 50. Put in your standard deviation of 4, and then the value 1. 1 wants the CDF, which is this. And that will give you the same result. Right? So, because I'm drawing this on my iPad, I can't bring up a z-score table. But if we bring up the z-score table, negative 2.5 equals 0.0062, and if I type in the code into Excel, this is something you can do along with me while you watch the video, and I type in 40, 50, 4, 1, I get the same value, 0.0062. And on the video, I'm not showing you these two pieces. There'll be another video that we'll show you later. But if you have the table in front of you, you can watch the video and see that you get these same results. Or you can bring up your Excel and see you get the same results. Now, the issue is the tables and Excel are all CDFs, cumulative distribution functions, which means I'm always finding the probability some random variable is less than equal to some event x. It's always less than or equal to, right? So if I draw my normal distribution for the one we just did, here's our 50. We wanted to find 40, right? Because we were doing the probability that some random variable is less than or equal to 40. Then this is the part of the curve we're finding. And that's why we can use the formulas and everything I have had posted before. However, if I want to find the probability some random variable is greater than or equal to 40, I'm still centered at 50 if I'm sticking with the same problem. 40 is over here, but I'm doing greater than or equal to, so now I'm on this side of the bell curve. Well, the table and Excels don't do that. But what I can do is I can do 1 minus the probability that x is less than or equal to 40. Right? That's a ugly less than or equal to sign. There we go. So in this case, I would just do 1 minus 0.0062. Which equals 0.9938 approximately. So you could do all the further steps. You just remember to subtract it from 1 if you're doing greater than. And then the other option is, if I wanted to find the probability of, say, 40 less than equal to x is less than equal to 60, given the same problem again. So I draw my bell curve. And I always like to draw pictures. Some of the homework problems will have you do it, but I always do it because it helps me make sure that what I'm solving makes sense. So here's my 40. Here's my 60. And since I'm finding in between, I'm finding these. Right? Well, how can I find that? Well, we already know this area is 0.0062 because we've done it a few times now. What I need to do is find from here over and then subtract this piece out, right? So if I go into Excel and I just put a 60 and a 40 in my code before, I get 0.9938, and then I'm going to subtract out 0.0062, right? Because if 9938 is from here, all of this, right? And then less than 40 is this piece. Well, you can see, what do? We counted that area kind of twice, right? So if I take that piece out, I'm only going to be left with the red. So if I subtract these two numbers, I get 0.9876. So that's kind of how a lot of things we're doing with this week. Now, the other different concept is the central limit theorem problem. Central limit theorem. Now let me change the color here so it's a little easier to see. Central limit theorem. Right? This allows us to take the sample of a population and make an inference about the sample mean. The key thing to remember here, your sample size must be, so n, little n is always your sample size, has to be greater than or equal to 30 if you're not sampling from something that follows a normal distribution. If you are sampling from a normal distribution, then we don't care about the sample size, right? Because in our course, everything basically is normal. But in the real world, that's not the case. A couple examples, life expectancy of a human follows a Weibull distribution, right? So life And it almost looks normal, but it starts out and then it has a long tail, right? So this is called a Weibull. And we don't really learn about this, but if you take an advanced statistics class, you will. And the reason is that when you're born, right, you have a great chance, you have to be very careful with a baby. It doesn't take a lot to injure it, A lot of babies die if they just fall. Then as you get older, right, you can take a little bit more. Like if you have siblings and you were the youngest, your older brother and sister might have just pushed you to the ground. No big deal. You got up angry, but nothing happened to you. So our life expectancy increases as we age. So this is our age. But then there is some part in our life where, again, falling down becomes very dangerous for us as we get older, and our life expectancy starts to drop. So it doesn't quite fit a normal. But if we take enough samples from this, say 50, which is greater than 30, the distribution of their averages will be normal. So this is our samples. Our sample averages, right? And that will be normally distributed. And what the central limit theorem says is the mean of this is the same. These two means are equal. The difference is whatever the standard deviation of this is, okay, well, the standard deviation of this will be the population standard deviation divided by the square root of n. And that is the big difference with the central limit theorem. So everything has a mean and a standard deviation. Now, how we learned how to calculate it was based on samples. We don't really get into how to calculate based on populations, but every known distribution, there is a lot of them, and again, we're only really learning the normal. However, there is lots of different distributions out there. And as you take from any distribution, for in this case the Weibull, and you have some standard deviation and some mean of your Weibull, so the average life expectancy of a human, depending on the country obviously, so we'll make up, say it's 73 with a standard deviation of 5 years, right? Then the average, if I take a sample of 50 people's deaths and I calculate their average, we expect their average to be 73. And if we keep doing that over and over again, we will build a normal distribution of the averages. Well, the deviation of the averages will be 5, because that's the standard deviation of the Weibull, divided by the square root of how many samples were taken, in this case 50. And that would be our new standard deviation. Now, once we have that information, and we'll go all the way back here to slide 1, we now see that we can apply everything that we've learned before. So the big difference between a normal probability distribution and something of the central limit theorem is this value right here changes based on the central limit theorem. But everything else is the same. When you go to use the codes in Excel, they're the same. You just have to calculate a new standard deviation. If you want to use the tables, they're the same. You just have to calculate a new standard deviation. If we're doing less than, that's that one. If we're doing greater than, same thing. You still find the norm, this, and you subtract it from 1. And if you're doing between, same thing. So nothing changes once you have your new standard deviation. All right. The key to knowing if you are doing something that requires a central limit theorem is this. If you're collecting a sample, so when you're reading the homeworks or any problem, and you want to find the probability of a single event, that what's the probability of picking one, then you do everything we did before. But if it says, what's the probability of something happen, and you're picking 30, then, or more, then that's the central limit theorem. So let's do a quick example here. So what would the probability of the sample mean of break and strength of a random sample of 30 rivets? So we have 30 rivets. And we want to know what's the probability that their sample mean, which is x bar, so the probability of x bar is between 500 and 700 psi. Well, to continue this, we know we sample 30, so there's our n. We don't know the mean, but say the mean is 600. Then you have everything you need to calculate, but you need to find a new standard deviation. So say our standard deviation is 100, right? And we're taking a sample of 30, so then our standard deviation of the sample mean would be 100 divided by the square root of 30. And then the mean of our sample mean is 600, because the central limit theorem says these two things are equal. And then to get to here, you have to apply the central limit theorem. Now, we have everything we need. We have our x's. So here's x1, here's x2, here is our mean, and here's our standard deviation. And you can go through and you can calculate these values. All right, I will post another video in the midweek announcement showing how to use technology better to solve these. This video is kind of more of the theory base to kind of understand the reading. All right, enjoy the week, and I'll talk to you online.